In this lesson, we're going to try and get a further understanding of the unit circle and try and get a more rigorous definition to it. So have a read of the learning goal, write another unit circle down, and we'll get going into it. So here we've got this unit circle, right? And we know typically we've got a y-axis and a cos-axis. And if we were to draw a point on the unit circle here, okay, out to the point P, we would see that we just need to go out some distance of the radius, right, which we know is a distance of 1. Now, and we've gone around some angle. Using that radius, kind of spun that radius around some angle to point it out there. And so whenever we're reading off a coordinate point here, we want to know where exactly is it in reference to the y-axis here, and where exactly here is it in reference to the x-axis. Now, what we can do here is we can actually draw down and notice that we get a right angle triangle when we do so, where this length here is going to be a length of y, and this length along here is going to be a length of x, okay, giving us our x and y coordinates that we initially wanted. So if we drew out the triangle further, and if you can just recall SOHCAHTOA, or sine is equal to opposite over hypotenuse, cos is equal to adjacent over hypotenuse, and tan is equal to opposite over adjacent, right? We can actually get some definitions out here, okay? Because if we took sine of this angle, what we would get is we'd take the opposite, which is y, divided by 1, that's the radius, right, or the hypotenuse. And what we've actually got here is we've got sine of the angle being equal to y, okay, which is, again, very nice. We can do a similar thing here for cos. So cos of theta is equal to the adjacent, which is x, over the hypotenuse, which is 1. We can make a deduction here that cos of theta is equal to x, which is, again, quite nice. We'll note that tan of theta is equal to y over x, which is the opposite of the triangle over the adjacent. And what we'll notice is, using some immediate substitution, y is sine and x is cos, so it's sine of theta over cos of theta, which gives us a nice definition for tan in terms of sine and cos. The reason this is valuable for us here is so that if we were to just consider another unit circle with all that information here, okay, is that instead of defining the x and y axis in terms of x and y, we can put them in respect with an angle that we're going to be given. And so whenever we are determining a point on the unit circle, we can, let's say if we wanted to determine this point right here, say here, the point P. The way in which we would do this is this point P is we can rotate the radius at a certain angle around, and we can determine the length of the x and y axis in terms of the angle, right? Because this distance here will now not be x, it'll be cos of theta, and this distance here will be sine of theta. So let's have a look at an example and see how it works. So I've got to show the point P, which is pi on 6, which that's 30 degrees, by the way. We're going to have to use some radian measure here. On the unit circle, hence state the coordinates. So let's take the point P with 30 degrees around, that's about here. And we're going to draw one unit out, which is our radius right here. That's a unit of 1. And we can see it forms a right angle triangle, which, again, 30 degrees, pi on 6. Now, typically, this coordinate point P has been at the point xy, but we haven't defined our axis in terms of xy, we've redefined it in terms of sine of theta and cos of theta, which means that this point P is at the point cos of theta and sine of theta. So if we want to determine where the point is, we just need to know the angle and we can find out where exactly it is on the unit circle. And so if you were to plug these into your calculator, right, you get cos of 30 degrees is 0.86 recurring, and sine of 30 degrees is 0.5. Exactly, it's exactly a half. So therefore, the coordinate point P is at 0.86 recurring and 0.5. I guess in other language, it goes along 0.86 units here and a half here. Now, this is nice, but what if I wanted to know the exact value of this one here? What if I wanted to know exactly? Okay, well, what I could do is I could draw out this triangle that I've got here. Okay, is that I could take the triangle that I've got there, and I know exactly this length here is a half, and I want to know exactly what this is. Well, to determine exactly, I can do this, I can use Pythagoras' theorem. So I would say that 1 squared is equal to a half squared plus, I'll use brackets there, plus something squared, and I would just simplify this one. Okay, so that means exactly this value here is going to be root 3 on 2. So, and you can double check this in your calculator, root 3 on 2 is actually 0.86 recurring, right? Which is nice. By a similar deduction, you can also, and we'll notice here that this is actually 60 degrees up here. So you've got that nice 30-60 triangle. There's another one with exact values. Okay, and so radius of 1, right? And now if it's at 45 degrees, that means it's isosceles. So this and this are the same thing. We can do a similar deduction using Pythagoras' theorem, but we've got 2 of the same thing. So you'd say that you've got 2 of this thing squared, and you would just rearrange and solve it. Okay, so you can determine the exact value is 1 on root 2. However, we normally like to rationalize our denominators. So we would say that it's root 2 on 2, okay, with a rationalized denominator. Looking at this second example here, we just want to illustrate that you don't have to always go clockwise of an angle around this unit circle. You can go anti-clockwise, and you can go around more than 360 degrees if you like. So here, illustrate sine of -30 and cos of 5 pi on 2 on a unit circle. If you're getting a little bit more familiar, okay, with these radius, you can pause it right now, you can try and work it out. Okay, but this is 450 degrees here. 450 degrees is big on 360, so we're rotating around this circle more than once. We'll identify sine of -30 first. Be going backwards 30 degrees, okay? Or another way to think about it is it's actually going around 330 degrees. Secondly, I'll do this one. Okay, secondly, I'll do this one in a different blue here. Cos of 450 degrees. Okay, you can imagine if you go around 360 degrees, you've done a full circle, and then you would just need to continue going around another 90 degrees. Okay, that's because 450 subtract 360 is equal to 90. So you go around another 90 degrees, and that would be this point. Okay, which would give us a right angle at 90